So this is a quick presentation on types of radiation. First off, what is radiation? Well, we'll start by saying that radiation can be things beyond ionizing radiation. Um, for example, light itself is radiation, and light goes beyond the visible light spectrum. So here is the electromagnetic spectrum for radiation. We have things like radio waves that you hear in your car, microwaves for cooking your hot dog. Infrared radiation it comes off of you and I. That's how we remove heat from our bodies. Then we have visible light. That's good for seeing. And then we have the ultraviolet light, which some of us aren't fans of, so we put on sunscreen if you're a pale guy like me. And then we get into the ionizing radiations in the light spectrum, and that's going to be your X-rays and gamma rays, which are, at least in my world, they're the same thing, with the exception of where they're born at. So then there's other kinds in the nuclear world of radiation that involve particles, such as alpha radiation. That's going to be your lightest source of radiation. It can still do damage to you, though. We'll get into that later. The next is going to be beta radiation, and this is true, but we'll get into why that's not the finest shield in the world, and using aluminum to stop it. And then we also have the scary ones that people are afraid of, gamma rays and X-rays. Gamma rays are present in every banana you eat, and X-rays you probably get every other time you go to the dentist office. Then we also have neutron rays. Those can be kind of scary, some might say, but they're less likely to interact with you on the bright side. So which makes them also harder to shield. Let's talk about natural radiation in the environment. So there's three there's three elements in four natural decay chains. First one's potassium-40. I don't really look at that very often, but it's in your banana. Anytime you eat a banana, you can get a little bit of gamma rays for you that morning. If you eat a banana in the morning. We got thorium-232. It's not in hammers. That's just because Thor. That one doesn't really interest me that much, but yeah, it's out there. And then we got uranium. That's kind of cool. U-235. Guys probably heard of uranium. It's used for nuclear reactors and weapons. U-235 is the interesting one. It fissions, but it also decays naturally via alpha emission. And U-238 decays naturally via alpha emission. There's also U-234 as a natural radiation emitter, but I didn't include it on here because that's part of the U-238 decay chain. That comes from U-238 decaying into thorium-234, which decays back up into U-234, which will then decay down. So these are your four isotopes that are naturally have natural decay chains, and then any natural radiation that also occurs after that is a daughter product of these four isotopes. These four isotopes that are still present on Earth, they come from the destruction of stars in the atmosphere in the early days of the universe, and they're present here on Earth. We're human beings, so if we can make it, we will make it. So we've made radiation sources ourselves. Here's a little image depicting nuclear fission. And what's going to happen in nuclear fission is we're going to get these radioactive isotopes here that are called fission products. We took U-235, let's say it's U-235, and we hit it with a neutron to make U-236. That became extremely unstable, and it burst apart into two isotopes. Pick your choice what they are, and those naturally don't want to exist, so they start trying to give off energy in the forms of radiation to get to a place where it's happy. Then I showed I believe this is the Mars rover Perseverance. Showed this one here because it uses what's called an RTG. It's an energy system that utilizes radioactive isotopes. It's used in space because it's not a very mechanical system. It's basically converts heat straight to electricity, but it uses plutonium-238, I believe, is the isotope. And the reason I'm calling that different than the fission products is because it's irradiated, and it's a transuranic. So anything that is an atom or is an element higher than uranium on the periodic table was produced by man, and it does not occur naturally. And plutonium does not occur naturally. It's made in a reactor. When a let's say U-238 doesn't split, catches a neutron, it's not likely to split. It's probably gonna become plutonium-239 after a couple decays. And that plutonium-239 or any plutonium-238 also shows up with a little bit of decaying. And those are useful, and in this case, plutonium-238 is useful in the Mars rover. And I also show here cobalt-60, but that's just an example of multiple isotopes that can be made in a nuclear reactor. That's cobalt-60 is a good gamma source, and that's why it was produced. They're producing less of it for security reasons, because other methods can be used instead of cobalt-60. But a lot of medicines are produced in reactors, and it's done by irradiating materials. Let's talk about alpha radiation. Alpha radiation is simply a helium nucleus that's 2 protons and 2 neutrons. Actually, in the nuclear world, protons and neutrons love being in this state. So in heavy atoms, they naturally form this helium nucleus inside the nucleus of a heavy atom. For this image shows uranium-235, which alpha decays, and then the atom quantum tunnels out of the nucleus and leaves behind the daughter product, in this case thorium-231, and it is now a charged ion that can interact with the environment and cause ionizing damage. Nice shield for alpha radiation is a piece of paper. That's because alpha radiation is relatively heavy in terms of radiation and relatively high charge. So it deposits all its energy pretty quickly. It can even be stopped with a dead layer of skin that's on one's body. So it's externally it's a fairly safe radiation, but you still want to minimize exposure because if it gets inside your system, it can cause serious damage. So just because uranium-235 only alpha decays, it doesn't mean you should walk up and lick it. Beyond the toxic properties of the uranium-235, you're still going to get alpha particles inside your body, and your body has not evolved to protect itself from alpha radiation, and you're going to get pretty sick. In fact, the Russians have used polonium-210, an alpha emitter, to kill a dissident Russian former KGB agent Alexander Letavinko by putting in his tea, and he drank the polonium-210, and he died shortly thereafter. Next one, beta radiation. Beta radiation is an electron or a positron that is born in the nucleus of an atom and then is ejected. Positrons, that might be a new word to someone. That is an antimatter. It is essentially an electron that has the opposite charge, has a positive charge. So the electron and positron are emitted, unlike the alpha particle, which has a distinct energy when it's emitted, it is emitted in an energy spectrum. And that's because with the electron and positron emission, they also emit a neutrino or an antineutrino, a neutrino being with an electron and an antineutrino being with an electron and a neutrino being with a positron. These are massless or essentially massless particles with no charge. They've, for the most part, can't be detected. The only reason we know that they exist is based on the energy spectrum that is observed from the electron. We can't predict with certainty it's not a distinct energy that's emitted from the electron, and they realized that some of this energy is being carried away by neutrinos and antineutrinos. often, I think in 6th grade, I was told a good shield for beta radiation was tinfoil. That's horrible advice, actually. Don't use that, guys. A little picture from the movie Signs. They're putting tinfoil on their heads to protect from the alien radiation. Maybe that'll work if it's radio waves. It's got a low emissivity. It might block the radio waves. But I'm not so sure it's gonna work if the aliens are using beta particles to hit them in the head, because that's gonna smack in there and it's gonna make an X-ray. It's gonna create Bremsstrahlung radiation, where the X-rays in the electrons in the tinfoil will want to break in the process of the beta particle wanting to stop. It'll give off its energy in terms of X-rays. So our friend Joaquin Phoenix here is gonna take a lot of X-rays to the head. Better choice might be plastics. Wouldn't necessarily use Legos. Might melt down the Legos and just make a plastic shield out of that on my own. But the Legos might work. So then we got X-rays and gamma rays. In my world, these are basically the same thing. Only difference being is this would be an example of an X-ray right here. This is a photon, an ionizing photon that's born from an electron transition. So if an electron gets liberated down here and it has to hop, and then the upper shell has to hop down to the lower energy state, it has to give off that energy to do that. And it does that in terms of emitting a high energy photon known as an X-ray. And this is a chest X-ray. Might do that at the doctor's office. Do it to your teeth all the time at the dentist. And these the scarier ones, just because the name is scarier, gamma rays. That's born in a nuclear transition. It really, frankly, they can have the same amount of energy. There's nothing inherently scary about a gamma ray than an X-ray. And they're just born in the nucleus, and it's a high energy photon. This is the Incredible Hulk. Supposedly, he was made from gamma rays. In reality, that'd probably just kill you. Don't get in gamma fields if you don't have to, guys. I use Lou Ferrigno because it's my slideshow. Good shield for this is lead brick. Lead brick is a nice shield. We use them all the time in our experiments, especially when counting. I like to use them when counting because they block out the little radiation that's around the room, so I don't get little counts from radiations that I don't want. So I'm only counting what I'm measuring, and it doesn't interfere with my experiment. Neutrons are very sad, in my opinion. I don't like them very much, but they're very useful. Neutrons can be born in fission products, as displayed in this image right here. Neutron comes into U-235. It makes 2 fission products, and then a few neutrons to go with it. And those are actually useful if you want to maintain a chain reaction, because now this neutron can go split another uranium-235 atom and keep the process going. But these neutrons are born fast. And the same for the ones born through fusion. They're born fast, and that makes them difficult to stop. You can't stop them right away. Good option for stopping them is water right here. I used Aquafina because I'm hoping to get a sponsorship by Pepsi. If you're watching this, Pepsi, hit me up. So the neutron comes in, it scatters around the water. Water doesn't want to absorb the neutron. It can absorb the neutron, but it really doesn't want to absorb the neutron. So it scatters it about because it has hydrogen in its molecule. And hydrogen is about the same size as the neutron. So it can impart more energy to the hydrogen, which is why it's used as a moderator inside nuclear power plants and nuclear reactors. You can also use graphite, and some reactors do that. In fact, a lot of the early plutonium producing reactors use graphite to slow down their neutrons. Now, if you want to absorb the neutron, you still have to absorb it, because thermal neutrons will just hit you, and that wouldn't be very fun. So maybe we use some boron. We also use cadmium, lithium, maybe helium-3. Suppose this is the picture of boron. Can't really tell the difference. It might be graphite, but on Google. It said it was boron. So that's going to absorb the neutron. So it's boron 10, and then it will split. Well, then it'll become boron 11, and that should alpha decay. And that'll get rid of my neutron. An alpha particle is a lot easier to deal with than a neutron. And it'll probably the alpha particle will probably die within my shield, my neutron shield, so I don't have to worry about that too much, the alpha particle. So good ways to protect yourself from radiation. Honestly, number one is distance. Distance is really good to energy spreads out across space. So the further away you are, the less dose you get. And then also time. All right, these once the material has decayed, it gives off radiation because the material is decaying. So if the material is decaying, then it also is disappearing. So if it has a super short half-life, yeah, it's going to put off a lot of radiation at that moment, but its activity levels won't stay high very long. So we might be able to wait out the radiation. And then lastly, sometimes you can't get away from it, and sometimes you can't wait for it to decay. So then we build a shield, and this is a wall. Maybe it's lead bricks right here. So yeah, that's a little bit of information on types of radiation and a quick intro into how to shield them.